Hi, my name is Sergio García. I am a double major student of Chemical Engineering and Physics at the Universidad de los Andes. Felipe Muñoz and I participate in the university's Product and Process Design Group and have been working in association with the local government. The purpose of this video is to present the work that I submitted to the annual SRA meeting. The work is entitled An Evaluation of Denser-than-Air Dispersion Models and was developed at the Universidad de los Andes. Let us first analyze the context and importance of this work. Colombia is a third world country in South America with over 45 million inhabitants. Bogotá is the capital of Colombia and it corresponds to the 25.3% of the gross national product. It is important to remark that Bogotá is a city surrounded by mountains with a great concentration of clouds in the metropolitan area. Additionally, Bogotá's characteristics such as weather, pressure, and wind conditions may have a great effect on the dispersion of denser-than-air gases because of its geography and global localization. Moreover, in Bogotá there are certain areas where a high density of toxic and flammable gases is concentrated. Due to the high amount of materials handled in these areas, they may be classified as high-risk zones. There is currently no knowledge or undergoing research with the capability of studying the dispersion of denser-than-air gas clouds in Bogotá or Colombia. These studies are not included in engineering programs all over the country, which highlights the importance of working with the local government to incorporate this type of elements in education and build a public policy for the administration of public risk. So why is it important to develop a project of this magnitude? At this time, Bogotá does not have a record of the amount of fluorine or ammonia being transported daily, and a possible leak or accident, depending on the material, will have a significant damage radius, with having an effect on both personnel and infrastructure. The main objective of the work was to propose, validate, and build technologies based on the existing models that will contribute to manage risk elements in Bogotá caused by industrial accidents that form toxic clouds of denser-than-air gases. So what exactly did we do to accomplish this objective? The first step was to study, revise, and select existing models for the evaluation of denser-than-air dispersion scenarios. Next, we designed and built a computer tool that will establish the behavior of the dispersion of a denser-than-air gas cloud. Subsequently, we decided to compare the obtained results with an existing CFD model. Why a CFD model? Computer fluid dynamic models are currently the best models to accurately describe the dispersion of denser-than-air gas clouds. So why doesn't the country simply buy a CFD model to incorporate in education? Because CFD models are currently outside the available budget for third world countries, and the objective is to provide the country with low-cost tools. The last step was to define the operability of the design tools. There are several existing models for the dispersion of denser-than-air gas clouds. However, the most common are box models, plume models, the Britton-McQuaid model, slab model, and CFD models. Box models assume the dense gas cloud has the shape of a flat circular cylinder with a uniform height and radius. Furthermore, this model assumes that the entire cloud volume has a uniform gas concentration. However, box models have limited applications due to their simplicity. In the articles Development of Dense Gas Dispersion Model for Emergency Preparedness and Simple Box Model for a Dense Gas in a Straight Sloping Channel, the authors used the box model to develop a denser-than-air dispersion model and conclude that the model accurately predicts vapor concentrations in the downwind direction and does not allow detailed modeling of all the physical phenomena contribution to the dilution of the cloud. However, it does recognize that there are two phases of slumping and dilution. On the other hand, plume models were originally proposed by OMS and were mainly used to calculate the path of lighter-than-air gases issuing from a column to the atmosphere. It was later extended to model denser-than-air gases. These models solve a component mass, momentum, and energy balance. The Britton-McQuaid model contains a set of nomograms which represent the concentration decay in releases from a continuous point source and an instantaneous cubic source as a function of downwind distance, and is very useful for calculations with an indicative purpose. The slab model describes the concentration in a cloud or plume by solving a one-dimensional set of conservation equations for mass, chemical compound concentration, energy, and the three components of momentum. Source can be a horizontal or vertical jet or an instantaneous release. Finally, CFD models are usually the most complex because they solve the 3D compressible Navier-Stokes equations. Furthermore, the model available to us uses the finite volume method as a discretization method. the simple method for pressure corrections, and the K-epsilon method for the turbulence. This CFD model follows a very specific methodology. First, you must construct an appropriate geometry, then you must define a simulation grid, and finally, the scenario must be designed. Following these steps, a proper model may be built and accurate results for the dispersion of denser than air gas clouds will be obtained. So what models did we select? Given the limitations and assumptions done by the box and plume models, they were discarded. So the next step was to design and program adequate computer tools with the Britter-McQuaid and SLAB models. But computer models are basically useless if the results are not validated. So how did we corroborate these results? Given the difficulties which may arise from conducting experiments, we needed a different validation method. So we took a CFD model that had been extensively validated as a safety tool to confirm the obtained results. Thus, we concluded that both the Britter-McQuaid and SLAB models provide an estimation of the dispersion of denser than air gas clouds. We have also provided an initiative to encourage the research and development of additional tools that could simulate other dispersion processes at a low cost. This research is also a kickoff for many other method improvement projects that would change the way that risk analysis is made in places with limited resources. As a future work, we have planned the introduction of a public policy for risk analysis and evaluation starting with Bogotá and preferably spreading it nationwide. We also wish to include this type of studies in engineering programs, both undergraduate and graduate, beginning with the Universidad de los Andes. Finally, given the limited resources nationwide, the idea is to allow college education to access these tools to promote their education at a low cost. What is the contribution of the work to modern risk analysis, engineering, and infrastructure research? My work will greatly impulse risk analysis when dealing with dangerous materials. The idea is to improve the transport, storage, and production of these materials to prevent the loss of workers and infrastructure. It is expected that this work awards risk analysis with the importance it merits. How is the research novel? How does the research advance knowledge in the chosen area? Considering the context of a third world country such as Colombia, the research comes as a new investigation. There is no previous work of this type with the government, and it will be the first major step to provide the capital with a public policy for risk analysis and evaluation. Furthermore, it is an incentive for other universities in Bogotá to adopt risk analysis to their engineering programs since it has become vital for engineers to consider safety first.